In this video, we are going to find out what reagents we need to go from this to that. And we have 3 problems to do. So we need to see here that the change, it looks like the bromine, instead of being in the terminal position, it had changed places. So when you see things like that, it often involves 2 reactions. One is an elimination reaction, and then you do an addition. You add that back. So what do we need to do? First, notice that also the number of carbons hasn't changed. So I have 1, 2, 3, and 4 carbons. 1, 2, 3, and 4 carbons. So effectively, the only change that we see is that the bromine is now into a different position. So to accomplish that, what we're going to do first is an elimination reaction. And to do that, I can do an E2 reaction, and in E2, we have choices of bases. But since I want to, this is fairly simple, elimination is at the end. I'm simply going to use, say, sodium ethoxide, or I can use sodium methoxide, for example. And at this point, what we want to do is do a beta elimination, which is an E2 reaction. If you need to check the mechanism, I have videos on that. But essentially what you're doing is abstracting one hydrogen at the beta position. This is alpha, this is beta, and you will be removing that to make the following alkene. So we have now no bromine atom. We have formed an alkene in that. So how do we make that the other compound? Now we need to add bromine back, but in what fashion? So what we need to see here is, again, the reagent that we need to be using. We see that we have added an H and a bromine here. So this addition had happened with Markovnikov reduced selectivity, meaning that the H has been added to the least substituted carbon in the bromine here. So all we need to add here is HBr. And for that, remember that in this mechanism, again, if you want to review it, I have videos about that. But what we're doing is essentially pi electrons acting as a base, abstracting the product. You form a carbocation, in this case, is secondary, and then bromide will do that. But notice again the sequence of changing the bromine from one terminal place to the other position involved 2 steps: an elimination reaction, a beta elimination, and then a Markovnikov addition, a hydrohalogenation. Let's look now at the second example. It looks similar in the way that, yes, we still have the same number of carbons, 1, 2, 3, and 4. And let's number it this way because these giving priority, when you name it, this will be 2-butanol. Okay, now the same number of carbons. The OH is now in a different position. So we need to do an elimination. However, we cannot directly use sodium ethoxide because OH is a terrible leaving group. And OH is a bad leaving group, so there are a couple ways in which we can do that. One way, if you want to perform an E2 reaction, we know that OH is a bad leaving group because this is a very strong base. It's the conjugate base of a weak acid. pKa of water is 15.7. So too bad as leaving group. So we need to convert that into a better leaving group. One way in which we can do that and do the E2 elimination is by adding here, doing the interchange of, say, change this for a better leaving group. We are transforming that into tosylate, which is a good leaving group. That way, we are going to be making the following. So this is replacing with tosylate chloride, replacing the OH by that. Okay, and that way, I'm far still from that. I'm going to have to erase something here. And probably it's going to be the last problem. I can copy that back. Again, because we still have a few steps to go to. Now, with this substrate, now we can do an elimination better because now we have a good leaving group. And how we can accomplish that? Again, if this is my alpha carbon, if that's my beta carbon, I will do a beta elimination. And from here, I can do, say, ethoxide, methoxide, any of those, and get the corresponding alkene, removing an H here and the OH there. So I'm gonna get, now here. This is butene, 1-butene. And then let's see what the change is when I go to this product. I need to add the OH here. And so that seems to me Markovnikov again, because for that, you're adding an H at the terminal position and then the OH here. So to do the Markovnikov hydration, you need to use diluted acid. Say that you use sulfuric acid diluted, and that way, remember that you will have hydronium in solution, and what you have is that pi electrons acting as a base. You will form a carbocation, so similar to the mechanism here, of course. And then you will have the attack, the nucleophilic attack by water to get the secondary alcohol. Another way that we use to make OH a better leaving group is using acidic conditions. However, in this case, we're not going to be using that because if we do this under acidic conditions and we do protonate this, we're not going to promote an E1 simply because there's a plus sign, because you will not form a primary carbocation. But this strategy would work if we had a secondary, or better yet, tertiary carbocation. So this path is not available here because we don't want to form it's unstable. We're not forming primary carbocation. So that path doesn't work. To do this reaction, we need to change the OH by OTS and do that reaction. So the other problem that I wrote is gonna be in another video.